Hello everyone. I'm Kailash, uh, PhD scholar from Nano DC Lab IIT Gandhinagar, and today we are with the live session 10, and today we'll be discussing about VHDL because in the last session when I have taken some of the questions on VHDL, I've seen that many of the students doesn't know actually what the basic constructs are and how to write a code in VHDL. Okay, today's session won't be an MCQ type where I'm having a question and we will be having a four options and we'll be solving them. Rather, what we will do today is I'll be designing at least four or five designs using VHDL, right? And I'll be telling you what are the syntax and how to write a digital design into VHDL language. So, as of now, what we have done is we have gone through all the basic designs in the digital design. We have started with microprocessor, but in between we had a topic that is called as hardware description language. Okay, where in the last session what we have done, we have seen couple of constructs of VHDL. Today I will take the opportunity to discuss with you in detail how to write a VHDL code. I hope many of you might know, but if you don't know, you can ask the questions at any moment of time. We will start with the very first. I have five examples for today, and I'll be starting with a very basic AND gate. We'll go on designing circuits like counters using VHDL. As of now, what you might have done is you might have designed all these basic circuits using gates or using Boolean expression. The same when how you will convert them into hardware is the way by which you have to write into hardware description language. VHDL is one of the languages, and this is how the construct look like. So any program you write in VHDL will have couple of components. Okay, so we will start with the first component, and at any time if you don't understand anything, let me know. Okay, so you see the very first component is using some of the libraries. Okay, so we have one library that is called IEEE. Okay, IEEE is the library, and use in the IEEE library what we are doing is we are using the standard logic. Okay, so the standard logic construct we are using because we have to use standard logic construct. So the very first thing which you have designed, you have to write while designing any of the digital design is you have to write about the library, what library you are going to use. The second part, which we have discussed in the last session also, and I'll be repeating again, is what we call as entity. Okay, you see in entity, what we do is we see our design as a black box, and what are the inputs and outputs of that black box is we will be defining in our entity. We will write the name of the entity and we will define what are the inputs and outputs are. In this example, what we are doing is we are designing an AND gate. You see, this is an AND gate. Okay, and we have two inputs, input 1 and input 2, and we have an output that is called as AND underscore result. So what we have done over here is we have defined the ports input 1 and input 2. Then what we have done is we have defined AND underscore result, right? So that is the port name. Okay, so the first part is the port name that you have to define. What are the names of the port? All the ports, whether it is an input, whether it is an output, or whether it is an in-out port, you have to define all the port names. After every port name, you have to define that what direction it is, whether it is an input port or it is an output port. Okay, so here you can observe that the input 1 and input 2 are input port. That is the reason why it is defined as input, while the AND result is an output port. That is the reason why it has been defined as an output. A- Along with that, you have to define that, okay, what kind of port or what kind of construct you want to use for that. And for that, what we do in VHDL is we define all the ports as logic type, right? So logic is a standard logic type by which if you define any variable, it can be used as both as input and output port. And to use this standard logic, we have to import the standard logic 1164 library. That is the reason why we have used this line. Okay, so you see over here is what we have done as of now is we have used the library, we have defined the library, we have defined our entity. Okay, in entity you write the name of the entity example and this is the construct. You write entity example and is, and then you define ports. Okay, and then end the entity name. So now what you have done, you have defined the ports of the black box. Now you have to define what is inside the black box. Okay, and that comes into the architecture. Okay, the name of the architecture which I have taken is RTL. You can take any name, and this architecture is of for which entity. Okay, so the name of the entity is example and, so you write example and over here, right? So architecture RTL of example and is, and then what you have to do is you have to define whatever logic you are defining. Okay, if you are using some intermediate signal, what you can do, you can write like this, signal and you can define standard logic. Please note that if you want to define a port, you define like this. However, if you want to define any intermediate signal, you can directly write signal and the name of the signal, colon, then you have to write what type it is, standard logic. Okay, it is not an input or output port, it's an intermediate signal, so there is no reason of defining input and output over here, right? So and then what you have to do, you have to write the logic here. How it has been written is you have taken input 1 and you have ended it to input 2. Okay, and you have defined it to AND gate. Okay, and then what you are doing is you are writing AND underscore result to AND gate. Okay, see, this is not an optimized code. You might have directly seen, right? You can tell me that instead of writing AND gate and then you define AND gate and then you write into AND result, what you could have done is you could have directly written AND result is equal to input 1 input underscore 1. So it won't be this. This is A and D, and the construct of AND is A and D space and then input 2. Right, but here I have intentionally put over this because just wanted to show you, if you want to use any intermediate signal, you can define like that. Okay, so you write rtl architecture RTL, the name of the architecture of which entity example and is, right, and you define whatever architecture you have, right? So this architecture is actually the logic what you are or digital design what you are designing, right? In this case, in our case, it was an AND gate. It can be anything. Okay, just to repeat what I have done or what I have shown you guys, what are the basic concepts, because if you understand this basic construct, you'll be able to write any code. Okay, so you won't be struggling with the construct as such. So first you define the library, then you define what entity it is, right? You define all the ports with name, then the direction, and then you define it is a standard logic. You do that, and then what you do, you define the actual architecture. In the architecture, what you have to do is you have to define what is the function, right? What is the function of your block, what you are defining. Okay, is there any question as such, how we are writing the VHDL code over here? Any questions?
No, sir.
No, sir.
Anybody else?
No, sir.
So what we will do is we will go to a much more complex example, is 2 is to 1 mux. Okay, so how does a 2 is to 1 mux works? What
4 is to 1, sir.
Sorry?
That is 4 is to 1, no, sir?
Yeah, it's a 4 is to 1 mux. Okay, so how the 4 is to 1 mux works? What you have to do is you have to define the select lines S1, then you have defined S2, and then you have Z. Okay, right? So if 0 0 0 1 1 0 and 1 1, right? If it is 0 0, according to this diagram, Z will be A. Similarly, for 0 1, it will be B. For 1 0, it will be C, and for 1 1, it will be D. Okay. Now, because I have already told you that what basic constructs look like, I do not have to go into much detail. It will be extremely simple. What you have to do is you have to define the library. Then you have to define the entity, right? The entity is mux 4 is to 1. Now you define all the input ports A, B, C, D. You can define in one line like this, okay? And then you define in. You have seen standard logic. Earlier it was written in small. It has been written in capital over here. So it is case insensitive, right? In whatever case you can write these keywords, right? But these are case sensitive. So A and B should be taken care. Is either small or greater, okay? Now you define the other two input ports. You could have written in one line, but it is better that you segregate the select lines and the input lines. And then you have one output port, that is Z, which has been defined as an output. Okay, and you write mux 4 is to 1. So the entity has been defined. Up to this is simple. Now what you have to do is you have to define, or you have to check, uh, or you have to write the code for multiplexer. For writing the code for multiplexer, you can see, right, it is an if else statement. Okay, when you design using an hardware, you have to write all the gates, but if you want to write using a VHDL code, you can directly write if else, just like what you write in C programming. So if you see, there are two signals, S0 and S1, right? If S0 is equal to 0 and S1 is also equal to 0, you write Z equal to A. Similarly, else if S0 equal to 1, then S1 equal to 0, you write Z equal to B, right? Similarly, S0 equal to 0, S1 equal to 1, you write Z equal to C, else Z equal to D, right? So you have written if else statement, but please note that it has been written under this statement, process. Okay, so process, anybody knows what does process means? Anybody want to tell me what does process means? Anyone?
It processes the things when sensitive list is changes. Any of the input signal or S0, S1 changes, it processes these things.
Right. So for other students, what happens is, if any of this input A, B, C, D, S0 or S1, if any of this input is changing, uh, what the process will do, process will allow you to get inside, and the statement inside the process will be executed. Okay, because it is a combinational logic. If any of the input changes, the output will bound to be changed, right? So that is the reason why we define process. And so here we have written process A, B, all the input you have to define, right? Because output is a function of input, so only inputs are has to be defined inside the process. And then what you do, you write all the if else statement, and then you write end process, and then whatever architecture you have defined here, it was behavior architecture, right? You have to end the architecture. Any doubt over here? Any doubts?
No, sir.
Any other student? Any doubt?
No, sir.
No, sir.
Yeah, few students, so I can ask everybody. Okay, then moving to the next example is a decoder. Okay, so see, what I am trying to do is I am trying to give you various kind of constructs which are available in VHDL. Okay, so here what we are trying to do is we are trying to design 2 is to 4 decoder. Okay, so if you want to design a 2 is to 4 decoder, uh, what you have to do, you have to have four inputs, right? So the four inputs b0, b1, b2, b3, right? You can define it as a in the form of a vector. Okay, so you can define b as a vector of 3 down to 0, right? Where b0 will represent the first one, right? B1 will represent the second one, right? Similarly, B2 will represent the third one, and B3 will represent the fourth one, just like this. Please note that the numbering starts from 0, right? Because it's a binary, okay? And what we will be doing over here, because as of now, whatever example we have seen, the output was a single output. In this case, we have multiple outputs, and we want to define it as a vector. Okay, so let us start with the writing the code, and I will explain. Consider this as a small a and this as a small b. right? That's how we have designed over here. Uh, this is the library which we have defined. It will be remaining same. Now, what you have to do, you have to define the port. So I have two ports, A and B, right? You will disagree with me because I have actually two input ports and four output ports. We have six ports, right? But let me tell you how to write these two ports into two lines using a vector. What you can do is you can write the name of the port A and B, and you write the direction, input and output. Okay, and then what you can do is you can write standard logic vector. Please note, earlier what you're design writing was standard logic. Now what you're writing is a standard logic vector. Okay, and then what you write is how much is the vector size. So here it has been written as 1 down to 0. 1 down to 0 means you write like this, a1 down to 0. It means you have two variables, that is a0 and a1, right? Similarly, if you write b3 down to 0, so it will be b3 down to 0. You have four variables, right? b0, b1, b2 and b3. Okay, so what we have done is we have defined all our input ports, all of our output ports using the form of a vector, right? And then what you do, you end the decoding design. Now what we are doing is we are defining the architecture over here again. So architecture is the logic, and please note that we have two inputs, right, and which has been clubbed in the form of a vector. So anytime a changes, I have to act, right? The output should be there. Okay, so what we have used is a process statement which has only one input, a. Okay, a is a vector of 2 bits. Okay, so actually we have two inputs. Then we have used a case statement. Okay, so how does a case works is whatever you write inside a case, this statement, okay, this will be compared against whatever write in you in this when statement. Okay, so generally case statements are being used like this: case x is, then you write when, you write y, and then you write some statement, when z, then some statement, when p, then some statement, right? So what will actually happen, as soon as the process there is some change in input, it will come inside, it will go in the x, and what will happen, this statement whatever I write over here will be executed if x is equal to y. Okay, similarly, if it is not equal to y, it will go to the next one. It will be executed if x is equal to z. Okay, so here how it is working is it is extremely simple. What you are doing is you are writing a. A is a 2-bit vector. A 1 down to 0. Okay, 1 down to 0, and both the bits will be compared. So if a1 and a0 it is 0 0, the b value will be 0 0 0 1. See, b value will be 0 0 0 1. What does it mean? It means that b3 will be 0, b2 will be 0, b1 will be 0, and b0 is equal to 1. Okay, and similarly for this case the b1 will be 1, for this case the b2 will be 1, and for this case the b3 will be 1. So you can write like this: case a is when 0 0, right? So a will be compared with 0 0. If that is true, you assign b, the vector b, as 0 0 0 1, and then you write all the statements, you end case, you end process, you end the behavior. Is that clear, everybody?
Yes, sir.
Yes, sir.
Okay, no doubts. Okay, excellent. So moving to the fourth part, again a very simple question, full adder. Okay, so you know that the S sum is nothing but A XOR B XOR C in, okay, and then the carry, the C out, is equal to AB plus BC plus C in, okay, where C is C in. Okay, it is like that. Okay, so what I have is sum Okay, so we have how many input and output vectors? We have five input and output vectors. So what you can do is you can define A, B, C in, S, and C out. You define everything, and then you write the behavioral code directly. Sum is equal to A XOR B XOR C in, C out equal to A and B, or C in and A, or C in and B. It's extremely simple. Okay, I hope there is no doubts, right? Because we have done this. So I've directly written whatever the statement I was saying. I've directly written over here the sum equal to A XOR B XOR C, and C out equal to A and B, or C in and A, or C in and B. Is that clear?
Yes, sir.
Anyone has any doubts? Anyone? Okay. So what I will do is I will go to next example. Okay. So can anybody tell me how this code is working? This code is for a VHDL binary counter. And by seeing this, can anybody tell me how this code works? Please look into the code and just tell me.
If it is pressed clear, it is the resets to 0000. When the clock is equal to 1, it increases its count plus 1.
Uh, is there anything special about this clock?
It's when clock is equal to 1, that means it must be a positive edge trigger.
Yes, right. So it's a positive trigger. It's not a combinational circuit. It's a sequential circuit which is triggered at positive edge, right? Is is it what you are saying?
Yeah,
Yeah.
yes.
Can you go through line number 10 to line number 22 and you tell me the meaning of each of the line? Just everybody understands. So that's the reason. Yeah.
Architecture of binary counter.
Yes.
Mm, logic with the 3 down to 0. Actually, I didn't got that. What is the 3 down to 0?
Okay. Okay.
Maybe it starts count from 3 to 0 or not.
Okay.
That is vector, four-bit vector.
Yeah, it's a
TMP is a vector, four-bit vector,
yes. Continue.
and it is a signal, and means it is TMP is a intermediate signal.
Yes.
Then process has two signals. One is clock and clear. Both are sensitive list.
Yes.
Whenever clock or clear changes, it begins the execution of that's remaining statements.
Okay.
If clear equal to 1, then TMP will be assigned to 0000.
Okay.
See, we are assigning TMP equal to 4 bits, hence we need to declare TMP as 3 down to 0.
Okay.
It means TMP takes 4-bit binary number.
Yes.
Else if clock event and clock equal to 1, it will be keep on incrementing, like temp is equals to temp plus 1.
Okay.
After the process, the temp will be assigned to Q.
Correct. I hope everybody understand the explanation. It was a very good explanation. I will just repeat what he has said. Okay. So the very first statements are remaining same. These are our libraries. Then what we have done, it's a binary counter. Okay. It's a binary counter. It means that so you can see the counter like this. It's a counter block, okay, which does the counting, which has a clock, okay, which is a positive edge triggered clock, okay, and it has a clear signal, okay, and it has an output Q, okay. This Q output will be of 3 bits, sorry, 4 bits, Q3 down to 0, okay, and this will go like this 0000, then 0001, and it will just keep on going, okay. So it will keep on counting. So that's what we want to design. So I have given.
Excuse me.
Sorry.
So can you please explain what is actually whenever 3 down to 0 means?
Okay. Whenever I say that it is 3 down to 0, it means I define a vector, right? So see, there are two things. Whether if you write just q is a 1 bit unit. Okay, q can only hold 1 bit. 1 bit means that it can be so suppose if you are designing a full adder, right, and you write sum equal to a XOR b XOR c, right? It is a 1 bit value, so you can write like that. However, if you are designing a counter, say, right, the output of the counter will be like this. Suppose it is a 5 bit counter or 6 bit counter, you will write output like this, right? Q5, Q4, Q3, Q2, Q1, and Q0. All of this will combinedly make the result, right? Because the output of the counter, if it is say 1, sorry, 0, 1, or 00111, like it is combinedly, it will be combined and it will be called as, okay, the output of the counter is 15, right? So whenever we want to define such kind of output, there are two ways. Whether the one way is you write all the 5 variables or 6 variables, q5, q4, q3, q2, q1, q0, in the form of the standard logic. The other way is what you do, you write q 5 down to 0. When you write q5 down to 0, you will have actually how many variables? 6 variables. The first variable is q5, the second variable is q4, and similarly you will have q0, right? So it is exactly similar to what we call as array in our C programming language or Python programming language, right? Where if you have to define many variables, whether what you do, you just vectorize it and you define like that. Is that clear?
Yeah, this is clear. Very thank you.
Okay, so down to 0 means it is just this we call as down to, right? So VHDL has made it like an English language, so you just write down to. Okay, is this clear with everybody? I hope everybody should be understanding, right, what a vector is. If you don't understand, please let me know. I will clear the doubt again.
Understood, sir.
Understood. Okay, excellent. So now what we are doing is we have a counter which should give a 4-bit output. So that is the reason why we have defined 3 down to 0, because we start with 0, right? So we defined with n minus 1. So yeah, clock, clear our signal, and then Q is my output signal. Okay. Now this is the name of my binary counter. I have defined as VHDL binary counter. See, whenever clock changes, what you have to do, you have to increment the counting. Whenever clear comes, you have to reset. Okay, that's how the counter is working, right? So if clear, the count will go to 0. Okay, if positive edge of the clock, okay, at that time what you have to do, you have to write q equal to q plus 1. It's like that. Okay, so instead of directly writing that, what I've done is I've used a temporary variable. What I will do is I will assign q equal to temp after every cycle, so that I will do. So this process, how does it will work? Anytime the clock or the clear signal changes, if clear is 1, right, it means you just reset it. Whatever the count the value is, you just reset it. Okay, you define the temp equal to 0. Please note that temp is a 4-bit vector. Okay, so temp is a 4-bit vector. It means you will have temp 3, temp 2, temp 1, and temp 0. Okay, temp 3, temp 2, temp 1, and temp 0. Okay, so you have cleared it. Now actual counting logic, how does it work is, else if, whenever you come up with a positive edge, okay, so to signify edge, we have event. Okay, so this will signify the edge, which as it is will be defined by this. If clock is 1, it means it is positive edge. If clock is 0, it means a negative edge. Okay, so this statement combinedly make a positive edge triggered flip-flop, right? You should appreciate the very VHDL language, right? How writing a one line can create a positive edge triggered flip-flop. Positive edge triggered flip-flop, right? If you write clock equal to 0, it will be negative edge, right? At every positive edge, what you have to do, you have to increment temp equal to temp plus 1. Okay, so the 0 0 0 0 will be incremented to 1, then at the second time it will be 2, then the third time it will be, at the third cycle it will be 3, and it will just keep on going, right? After the value reaches 1 1 1 1, it will again reset. By default it will reset, because what you have done is you have defined q as 4 bits, right? Because if you define q as 4 bit, the bit will be gone, right? So if you add 1111 plus 1, it will be 1 or down to 0. So only the 4 bit will be stored, the fifth will be just, it will be ignored, right? And it will start counting from again. Okay, so at every 16th cycle, right, at every 16th cycle the counter will restart again, right, automatically. However, if you want to restart at any time between, what you have to do, you have to just provide a clear signal. You provide clear equal to 1, the output will be 0. The output will be 0. And what we have done, we have defined the temporary signal, and after that you just write q equal to temp. So whatever the value of the temp is, it will be assigned to q. Is there any doubt in this part?
Yes, sir. Sir, here we have used positive edge trigger, right? So in few cases, we will be using both positive edge and negative edge. Like in Verilog language, we will use pos edge or neg edge in the sensitivity list. So here, how do we include that, sir?
A posage or negate?
Yes, sir.
See,
Both. Like if you want to vary it with respect to positive edge and negative edge, then how should we include that?
okay. So let me tell you a couple of do and don'ts of the hardware description language. Okay, right? So if you want to define a posage, you can define like this. Okay, so what you do, you define like this: clock event and clock equal to 1, right? Or you write a bracket, okay, and then you write clock event and clock equal to 0. Okay, you write like this generally,
Okay, sir.
but what will happen is you never want to write a posage and negage of the same signal in a Verilog or VHDL language, right? So that is a criminal offense, you can say, right? Otherwise it will generate an extremely complex hardware, uh, if you define like this. Okay, so this is not suggested, but if you have asked, I'm just saying that generally whenever we write both posage and negage in the same sensitivity list, it is for different signals. If you can write clock as posage and the reset as negage, you can do that, right? But having the same what you say, same signal with both the edging is not advisable in hardware description language. Whenever you synthesize the design, it will result into a highly complex logic, right? Which is generally not synthesizable. Okay,
Okay, sir.
now I have discussed about synthesis. Anybody knows what a synthesis is? What do you mean by synthesis? I will ask lot of questions because there are few students, and I just want to make sure that you understand everything about hardware description language. How does it will be converted into hardware and all? Anybody knows what a synthesis is? Anyone? So let me write the spelling of the synthesis for you. This is what I am talking about. Synthesis. We have couple of more terms over here. Okay, simulation. Okay, then we have synthesis. What do you mean by simulation and what do you mean by synthesis? Anyone? Anybody? Anybody knows? Can you write on the chat box that if you don't know, you can reverse the process of the design? Okay, so is this for synthesis, Madhubana? Okay, so I am actually not getting what you are saying. Yeah, can you unmute and can you tell?
That means if you have an idea and we are getting that's converting that into a product, that means we can say it's a design. If you have some product or if you have some thing, finding how it works, we can say that's a synthesis.
Okay, okay. So
Maybe, I don't know.
okay, okay. I will discuss about these two terms. Now, Bhavna is saying, I think she has written about the simulation. What she says that verifying the output of the design using test bench. So that's absolutely correct. Okay. So simulation means you write a test bench. Okay. And you verify this design whether it is working correctly or not. And how do you write a test bench? You provide all the inputs over there of these things, and you check the output using what we call as a simulator. Okay. So there is one simulator which is online and everybody should use it. Okay. And this is called as EDA Playground. Okay. EDA Playground. This is open source simulator. You can use it. If you are in a college and the college provide licenses for you, you can use Xilinx Vivado. Xilinx Vivado. Okay. So this is from Xilinx. This is a tool which can do simulation synthesis for what we call as FPGA, Field Programmable Gate Array. And you have another tool, two tools actually. One from Cadence. Cadence is one of the other companies. And you have a tool which is called NC Simulator. Okay, you should write this name even if you don't have access this tool, but you should know, right, how you can simulate your Verilog design or VHDL design or system Verilog design, any hardware description language. And there is one more company that is called a Synopsys, and they have a tool that is called VCS, right? Synopsys VCS. So see, these three are industrial level tool. If you go to any of this, any of the industry, let's say, right, you are working in Intel, you are working in say ARM, AMD, you might be using one of these three tools for doing synthesis, simulation, and implementation. Okay, so what do you mean by simulation? You just write a test bench which will help you to test your design, right? Whether for all the inputs you are getting correct outputs or not. What do you mean by synthesis? I think Bhavna has answered this question also. What she is saying that creating a netlist of design to implement it on the hardware. So so many terms over there, but if you guys understand, it is fine. If you don't understand, let me tell you. So see, whatever you have done over here, you have just written a very low code. Okay, so this is RTL netlist. Okay, this is a very high level netlist which you have written in VHDL, right? What you want to do, you want to convert this netlist into what we call as standard cells. Okay, this is a very technology specific term or a VLSI specific term. What are these standard cells? These are AND gates, OR gates, right? Or not, XOR. There are other gates which are called as AOI gates, and or invert. Okay, OAI gates. See, whenever you will get any technology means you might have heard about 5 nanometer, 7 nanometer, 28 nanometer, right? Have you ever thought that how these chips are designed and what are the components that have been used over there? Is it like that you only write the very low code and it will be just converted into chip? The answer is no. Every foundry or wherever these chips are fabricated, what they do, they provide us these standard cells that whatever code you are writing, you write all this code, doesn't matter. You have to eventually convert in the form of these gates. Okay, whatever gates they have provided, right? Otherwise, they won't be able to fabricate it. So our goal is to convert this into in the form of this gate. and this process is called as synthesis. Now the question is, who will do this synthesis? Whether you will do manually convert all the gates or all the design into Verilog, from Verilog to standard cell. The answer is no, because it is a very tedious task, right, to convert your design into this standard cells. Because writing in this form is extremely easy, but imagine if you have to write the counter in the form of gates, right? It is extremely difficult. So for you, there are tools which are available, which are called synthesizers or synthesis tools. Okay. From Xilinx, you have again the Xilinx Vivado can do the synthesis for you. And from Cadence, you have one tool that is called a Genus. Okay, please note these names. These are extremely important for you guys. And from Synopsys, one of the very famous tools which you have is what we call a design compiler. Okay, design compiler. So how to do synthesis? You just provide the entire Verilog netlist, this whatever you have written, and you provide the technology information that has been provided by the found where whatever the information they have provided, they will tell that okay, these are the gates which you have. Then you make whatever logic you have using these gates only. Please note that many of these gates are universal gate, so any of the logic can be implemented using these gates, right? So converting this Verilog netlist in the form of the standard cells, this is a new term for you guys. Okay, standard cells. So standard cells are the basic building block of any circuit design or any digital design. Okay, so these are nothing but all the gates which have been provided. The converting the Verilog or VHDL code from the RTL level to standard cell level is what we call as the process of synthesis. Everybody understand this? Everyone, please confirm if you understand this. Okay, if you understand, I have used this term RTL. Can anybody tell me what is the meaning of RTL?
Register transfer logic.
What does it mean? Register transfer logic. That is absolutely correct. Register transfer logic.
So it uses different logic voltage for 0 and 1s.
Different logic voltage for 0 and 1. Why do we
Ones, yeah.
call this as RTL? So that's my point. Anyone wants to answer this? These are some of the important questions you have to understand. Yeah. Anyone? Okay. So this is what we call as register transfer logic, and the meaning of the register transfer logic is you are defining whatever the circuit in the form of a behavioral flow, right? In the full form of a flow of a digital signal, right? How does the signal is flowing? Flow of a digital signal, right? Whenever you define logic or whatever logic you have in the flow of a digital signal at a very higher abstraction level, right? You're not defining all the AND gates, NOR gates like that, but you're defining in the form of a very abstraction level where you're just saying that okay, if this is my input signal, this is what output should be. Okay, and you define in terms of logic blocks. This is called as register transfer logic. Okay, and this is what we call as RTL. So whatever code we write, we call as RTL code. Okay, and converting this into standard cell, this code is again what we call as technology dependent technology dependent RTL. Okay, so because now the code will be written in the form of AND gate, NOR gates, XOR gates, and all. Okay, so this was one of the very important things. I have one more question for you guys. I have told you about 7 nanometer, 5 nanometer, right? 28 nanometer. We also have 180 nanometer. Anybody wants to comment on this? What does this mean? Anyone? Anybody knows? Uh, Anyone? Can you come?
Don't know, sir.
Okay.
No, sir, don't know.
So what you should do, you should do an exercise. You search your mobile phone, okay, the processor of your mobile phone. So suppose if you have an Apple mobile phone, the processor will be mostly M1 or M1 Pro, right? If you have a Samsung or if you have Samsung mobile phone or any other company's mobile phone, the processor will be mostly Exynos or Snapdragon, okay? Or you can have a MediaTek processor, MediaTek, right? So these are the three processors which are generally available for mobile. If you have say Apple mobile phone, the processor will be M1. If you have a laptop, right, the processor will be Ryzen, okay, or I series, okay, i3, i5, i9, okay, i7, i9, so this will be right. So these are the name of the processor, but what you have to search at which technologies these are made, at which technology, okay. So the transistors by which all these processors, all these circuits are made are associated with a particular technology. Currently, all the recent mobile phones or the most recent processors are actually made in the 5 nanometer technology, right? So this is the name of the technology that has been given. You say, is there any significance of 5 nanometer? Currently, actually not. In earlier days, in the good old days, when we had 90 nanometer technology, this 90 nanometer or 180 nanometer actually used to denote what we call as channel length of your uh, the basic building block, which is called as MOSFET. Okay, so in the digital design, currently we have only focused on gates, or the basic abstraction was up to gates. Okay, just to give you an idea, if you look an inverter, it will look like this. But if you break down into a CMOS logic, the inverter looks like this. Okay, inverter looks like this. Many of you might have heard of this, but many of you might not. Okay, this is how an inverter looks like. If this is an input, this is output. Actually, inverter looks like this, input and output, right? And this is what we call as PMOS or P-type MOSFET, and this is what we call as NMOS. Okay, and how does it work is, when you provide 0, this PMOS only works when the input is 0. NMOS only works when the input is 1. Okay, and this is VDD. VDD means logic 1. Ground means logic 0. And whenever it is 0, this PMOS gets activated. The 1 comes over here and this is off. The output is 1. Similarly, when you have 1 over here, PMOS is deactivated, right? NMOS is activated. This 0 comes here. And this is how the inverter is actually implemented, right? And one of the property of this MOSFET is what we call a channel length, right? And the channel length of the MOSFET was earlier used to define what technology is. The lower the channel length, the faster the transistors will be, because it will have more current and high performance, right? I'm understanding that I'm saying a lot of terms, but you should just know some brief of it, how actually your gates are made up of. Okay, so that was the reason I just brought out these things, because these are some of the things which are happening in the semiconductor and the VLSI industry. Every year a new technology comes, right? People are working in 3 nanometer. Samsung is working on 3 nanometer. So as a VLSI engineer, as a semiconductor engineer, you should know what this technology mean. Okay, whenever you get a processor or whenever you buy an electronics, As an electronics enthusiast, your goal should be, okay, how does this processor is being made? What is which company has made? What is the type of the processor? What is the bit of the processor? What is new in this processor? These are some of the questions. If you will ask from yourself, you will appreciate whatever the design you are making, and you will appreciate the field of digital design. You will appreciate the field of VLSI. Okay, I'm just motivating you guys to and just giving you some direction how to go ahead in this field. You go ahead, you search any electronics name, you dig deep inside how it is made, what is the processor it is being used, how fast it is when we compare with the other processor, how power efficient it is, right? Why there is power efficient as compared to the previous generation? Why at every 3 years or every 2 years there is a new processor which is coming out? Every 1 year there is a new processor which is coming out at the same price of the previous one, right? How people are doing that, right? If you will ask this question, you will get interested, and at some time in future you might be the one who are designing this kind of processor. Okay, so I think that's all from my side for today. If you guys have any question, feel free to ask, or we will meet next Tuesday, same time, and we'll be discussing more about the microcontrollers and the microprocessor, and we'll be discussing about the assembly languages and some of the questions on the assembly language. Any questions from your side? No doubt. Okay. Anybody else? Uh, link of the recording session. Let me share you. I will share it to you right away. Just 1 minute. So this is the playlist where all the recording sessions are uploaded. Okay, so you can go watch all the session, and just prepare hard for your exam, and also be motivated to take up this as your future VLSI field. Okay, future field. So thank you everyone for joining. We will meet next Tuesday, same time from 6 p.m. to 7 p.m.